First of all, thank you, Evan, Jermaine, Rick, and Vasilis for putting this together and for inviting me. Thanks you all for coming. When I was invited, we were invited to give a bit of an overview talk of topics we're interested in. So I thought I'd go over these, or pick these 3 papers from this year, because they are related to different aspects or represent the topics that I'm interested in, which would be Gaussian states, their entanglement structure in different contexts, signaling entanglement harvesting with our beloved Unruh-DeWitt detectors in RQI, and also non-perturbative methods for matter-light interactions, but also again for detectors and fields. And so when I prepared this talk and I looked at what I had promised in the abstract, and then I looked at the 20 minutes that I have, I realized, oops, I was maybe promising a little too much. So to not fall into this trap of, talking a lot about the first article and then a little about the second and way too little about the third, I thought I'd go the other way around. I would start by talking about this third article and say too little about it, and then I will say a little more about the middle one. And finally, I want to focus on this one, which is chain mappings methods for relativistic light-matter interactions, because I hope that there for you, where say you and think of the RQI community, there may be some new ideas or methods we could use in there. So let me start with really just one brief slide on this one, which is to appear next week. Probably a rushed collaborator is hacking this on the archive right now. This is with Erik Aurel from KTH, Lukas Hackel, and Mario Kibok in Melbourne, and Pavel Hodoletsky in Gdansk. And so what we do here is we look at families of random pure Gaussian states. So we say, well, let's look at the family of all pure Gaussian states, n-mode Gaussian states, which all share a certain set of specified marginal states, and then take a random hair unit measure over those. And that's a cool and interesting family that, we were lucky to have Mario Kibok on board, who knows a lot of random matrix theory. But then our motivation was to, how we got into this, more questions about black hole radiation, and we think that maybe there is also a nice intuition building or some lesson to that maybe could contribute there to the big problems there. So stay tuned for that if you're interested next week. And the second paper, and here I will say a little more, is about entanglement harvesting near 3 + 1 dimensional Schwarzschild black holes. That's basically a follow-up to an earlier paper we had with Mark and another students of his, where we looked first at signaling. And it's related to all, the interesting things that happen when you are close to a black hole. And here, and this actually is, this article relates to the title that I put on my talk for numerical methods, because here Joao Caribe and Mark Casals did all the hard numerical work that goes into calculating the green function that you need to get to calculate entanglement harvesting and signaling between detectors. And yeah, so here is the video that's missing, so I will try to dance it for you. The question is, what happens close to a black hole? So what was going to be happening here was that you would see a black hole in the middle, and you would see Alice here. And then from Alice there would emanate a light cone, and whereas in space, in flat space-time, this would just spherical a ball just expanding. What happens if you have a black hole in the middle is that this ball starts to expand, but then it starts to fold around the black hole, and it starts to see itself again. It intersects with itself. That's where caustics form. And then when it goes the other way around, there's even again a point where you have another meeting point, so again caustics form. And so you get this involved structure of null geodesics sort of winding all around the black hole, opening up for different paths on which information signals can travel from Alice to Bob. And also this is interesting thing of when you do this, that every time the light cone goes through caustic, the singularity structure of the Green's function changes, changes. So, it changes, and on top of that, you always have the Green's function being supported not only on the light cone, but also inside the light cone. Strong-Huygens principle breaks down, so you also have these tail contributions that you all need to take account. So to sum this up, calculating the Green function gets really complicated, and that is nevertheless what Mark and Joao were able to do. And I'll just quickly give you an overview of what we did. We considered the Bulba, Hartle-Hawking, and Unruh states. They really all behave very similar for the questions that we looked at. only some minor differences due to the expected differences in the different noise the single detector sees in these states. And what we found is that this gravitational lensing of the light cone close to black holes really allows for entanglement harvesting to appear there again. Now, why would that be maybe surprising at all? I picked this one figure to illustrate it. So again, we have Alice sitting here close to the black hole, I think at 6m, radius 6m, and then a bunch of bobs sitting around at different angles, also at the same radius. And if we pick a bob that sits close, then what do we see here? Well, after some propagation time, a strong signal comes in. These blue lines measure the correlations between the two detectors. So we see the correlations overcome the background noise, and what this means for you as an easy takeaways, here the detectors can get entangled due to the interaction with the field. Now if you move Bob further away, then he may still be able to get a signal and overcome the noise, but here there's somehow a darker shadow corner, say 3/4 pi. There is some signal coming in after a time, but it doesn't overcome any longer the local noise, so these two detectors, when you couple them and decouple them again, they would be in a separable state, not entangled. And now, in Minkowski spacetime, of course, if you're at that point and then you move the detectors even further apart, well, we get less and less of a stronger signal. Not so here. If you go to the antipodal point, you see that there where these caustics form and suddenly light rays hit Bob all the way from Alice, the signal again gets pretty strong. So you see, well, again, these two detectors can be entangled. And if you're like to the connoisseurs or the experts in the audience, what we also found is that there are both regions where, well, most of this entanglement should be associated to communication or signaling, but also shortly after the caustic you find setups where really you can tell that this entanglement is extracted from the field. It's pre-existing vacuum entanglement that is swapped out of the field and onto the detectors. All of that to be found in that paper. And now the thing that I want to focus on most today is this work from this summer with Johannes, who's we were colleagues at Munich. Yeah, there it is. And now he is at the ETH in Zurich. And here we used chain mapping methods. We had also another project where we used them to look non-perturbatively at strong interactions, or ultra-strong interactions for so-called giant atoms. That's a quantum optical setup. And this one would be the other where we applied this to relativistic fields. Wanted to check out what we would be able to achieve there. And we picked as a demonstration for this Unruh radiations, the question, okay, what radiation is emitted from a uniformly accelerated emitter atom or particle detector? So the takeaway I hope for you would be that, well, maybe, but both conceptually see what these chain transformations actually are, because they, I think, are already interesting when just conceptually when you're thinking about matter-light interaction, but then also to see what numerically you can achieve with them. So what are these starter chain transformations? Well, the idea is to cast an interaction between which looks like a star. So we have a system, in our case the detector, which couples linear to a bath, to rewrite it exactly in a form that it takes this shape of a chain. Because in this shape, it's very amenable or very well suited to apply DMRG, matrix product state methods to it. Full stop. And so these transformations are widely known and widely used, in particular for open quantum systems. And depending on the community, they will go by different names. You can look for Cholesky transformations, T-DOPA, reaction coordinate mapping. And typically, what is done is that people are most interested on observables in the system, not so much about what the bath does or observables on there. But that's what we wanted to get at. We wanted to keep track of the bath and in particular evaluate radiation that is an observable on the bath and see what we could achieve there. Now I said linear interaction. What do I mean by that? I mean that the interaction Hamiltonian between the system, here we have our sigma x operator, but that doesn't really matter, can be any operator here, that the interaction between system and bath is given by a simple tensor product, where here on the field, the bath, the waveguide side, you have an observable which is linear in creation and annihilation operators. Right, so that's why this is a star shape. We have the system talking individually to each of the eigenmodes of the field, which is a bath of harmonic oscillators. Now what I can do is I can take all these modes together, right? I can take this term here and take it to define a new mode. Let's call it C0. And I have to normalize it properly, but what it does is it recasts our interaction Hamiltonian into our system with a slightly different coupling now, but talking to only one mode of the field. If I now go on, I look at, okay, what does this mode couple to in the other than the system in the field, and then what does this mode couple to, and so on. So I apply this Cholesky transformation, tridiagonalization really of the Hamiltonian matrix. This is what I end up with. We have the system talking through the old interaction Hamiltonian, but now to only one mode. And in here we have hopping terms only. And what is important is that these modes here, the chain modes, share the same vacuum as the initial modes. The Bogoliubov transformation between them is non-mixing, so particle preserving. And this transformation is exact. If you have n modes here, you end up with n modes in the chain. If you have infinitely here or a continuous path, you end up with infinitely many modes here, typically. Which is great, and at that point you can work conceptually. If you want to put it on a computer, of course, you can only treat finitely many modes. So you have to truncate the chain, and that introduces some errors. But you can well control them. In particular, if you start out in the vacuum and you do some excitation here, you can be sure that as long as this excitation hasn't reached down and maybe reflected back into your system, that you're actually treating the full exact system. You haven't introduced any UV cutoff or other cutoffs that may introduce causality problems, which we're usually fighting with when we want to look at a relativistic scenario fully. So that's what I found very appealing about these. Depending on the numeric methods that you use, more problems may come in. When we put in harmonic oscillator here, of course, we treated this whole thing just with Gaussian methods, and they can be very precise numerically. When you do MPS, I will show you more problems show up because, just as numerical errors from your method. Now here I pointed out this works for the vacuum. What do we do? I mentioned Unruh effect. What do we do for thermal states? Well, even there you can do something. See if your system couples to a bunch of states, which here are in a thermal state. That's what we indicate with this red one. We can play the thermodouble field state trick. We can add a negative energy copy of our system. So to each of the eigenmodes here, I now just add another mode. It has the inverted frequency. And I choose the joint state of these mode pairs such that they are in a two-mode squeezed states, so pure state, each of these pairs. But if I take only one, then this is in a thermal state. And now I can take each of these two modes, I can unsqueeze them, so to speak, and then I end up with now my system talking to, twice as many modes, but all of them being in the vacuum in the ground state. And from here then, and under this transformation, the Hamiltonian doesn't change shape. And at this point, we are back in the old game. We can now do a chain transformation and again run the same kind of methods here. So what then did we find, or how did we apply this to the Unruh effect? Maybe this, if you know the Unruh effect already, sort of looked familiar to you, and that intuition is exactly right, because in the Unruh effect, the role of these modes is basically played by the Rindler modes and the Unruh modes. So what did we do here to model this thing? We were interested in the radiation that a particle detector that we drag along the uniformly accelerated world line would emit into the field. So our interaction Hamiltonian now looks like this. This is basically, if it's a two-level system, that's the Pauli X operator. If it's a harmonic oscillator, then that would be one of the quadratures, Q, say. And we coupled it to the field at, this should be in convention pi, because it's the field, the momentum of a massless scalar field in 1 + 1 Minkowski space. And we smear this function out, we smear this coupling out by a Lorentzian. Now for the experts, why did I use a Lorentzian? We have that point in the paper. At some point, certain integrals were just solvable for the Lorentzian, in the thermal case, where there was no solution known for the Gaussian, which would, of course, be nicer to use in the first place. So, but to make this work, a Lorentzian there. And then, if you then put this model basically into Rindler coordinates, you drag it along this world line here, then you see that naturally your detector here comes to Rindler modes, so that's where we started from, made this transformation, oh great, and did chain simulations. So what did we find there? Well, I mean, this is just a picture to show that we did it for us to look at jointly, but maybe to give you some details on how far we could go with this. What you see here is plots for harmonic oscillator emitters and for two-level systems, either starting in the ground state or in the excited or one-particle state of the detector, and the radiation profile that was emitted to the left and to the right from this detector. So you see, for example, this bump here is when we switch off the detector. Of course, we sort of rip it out of the field. That leaves energy density behind in the field. And the other bump here, that's from switching on the detector. But here in the middle, we have oscillatory features that are somewhere from in the middle. Acceleration here wasn't very strong. L times the acceleration of the detector is the length scale of the Lorentzian is just 1/10. And how long did we calculate this for? Well, we started them off at proper time minus 7L. And here we were limited by the length of the chain. We used 250 chain modes for this. And so we analyzed it, well, after 7L simulation time, our excitations hit the end and reflected back, so we wanted to end there. And another model is another limit of this model is, of course, that this product can never be too large, otherwise you're really unrealistically smearing out the detector way too far into acceleration regions of very high acceleration. Here in a log plot, now only the harmonic oscillator for higher and higher oscillations. You see there accelerations, you see they're rather regular. You also have a nice symmetry between left and right moving radiation, and in fact you can show that this has to be that way. And what we found now, whereas these are evaluated directly from the as rather complicated observables from these chain that we obtained when we started with the thermal state, we found that at these lower accelerations still, you can really understand this emitted energy density profile by looking at what a detector at rest would emit and Lorentz boosted correctly. So from the relativistic side, that maybe is a little boring because really nothing very unexpected happened there. On the other hand, if you look at the method, it's quite, assuring to see that these very different calculations to very high precision coincided here. These things here, highly frequent oscillatory patterns, they point towards the problems. These seem to be error signatures. We have a longer discussion in the paper of what happens when your excitations hit the end. Thank you. At the end of the chain. So that's one problem. And how soon your observables are dependent on such errors depends, of course, where on the chain they live. If you think of system observables, you have much longer simulation time before they get affected. If you you look at the energy density, you need to be very careful very soon. So depending on what observable you look at, you may be able to derive observable dependent error bounds. That would be an open question. And then I mentioned that matrix product state methods can be sensitive earlier, and to illustrate that, they, for example, have to look at what time step in your, what time trotter step in your discretized time evolution is the optimal one to use. So to illustrate this is a case where we have free field, so this energy density should propagate undisturbed from the left to the right. This sort of worked, or this worked for time steps 10 to the minus 3L. If you go for longer time steps, you see that there is a large deformation kicking in very few. But shorter time steps aren't always better, and we can explain why. It's like a Zeno-like effect. You see that here, even after some time steps have, early on, there are bad perturbations or error terms appearing in these energy densities. So here there's an extra, you need to worry much more about your numerical parameters in this case. So this certainly goes into the outlook on what is left to be done. What would be very cool now, I think, would be to look at 2 and more emitters. Again, maybe do entanglement harvesting and communication scenarios with this. And there's also some math work left to be done. Not so much maybe when you start out with a discretized bath, but when you do it for continuous baths. So one emitter you can directly connect to the theory of orthogonal polynomials. For two emitters, it will work, but mathematically I think it's still interesting to work that out. I mentioned the error bounds for bath observables, and then of course what's left to be done is compare this to other alternatives. Quantum optics has many more approaches and methods to offer. And also, for example, this question of the Unruh radiation has of course been treated in certain approach or works, also analytically non-perturbative already. So there's a lot to benchmark against there. So with that, thank you for your attention, and here an overview of all the works I tried to make you interested in.
Thank you, Robert. So now, do we have any questions?
I just have two short ones. So one is that higher dimensions, there's no DMRG, right? Or at least there's no equivalent of DMRG that works.
No, that works. I mean, this is we here use 1 + 1 dimension, but this carries through for any dimension. It really only depends on your coupling here being linear, and that applies also for higher dimensions. The point is, I mean, this can be in higher dimensions, but the chain you get is one-dimensional if you have one emitter.
Okay. And the second thing is that, do you know if anything that, so this is kind of like from open quantum system kind of tricks, right? But there's another thing that people like to do, which is the Polaron transformation. Do you know if there's something you can do here?
This got us started to read up on the Polaron transformation, but
basically you reshuffle strong coupling with the detector into the bus so that the detector now couples weakly to the rest that has got reshuffled. Yeah,
I mean, Polaron transformation would be like an expansion from 1 over lambda, right? I mean, come from strong coupling and going in there. So we have actually had some discussion. I mean, I'm aware of this. I mean, but Polaron is still an approximation, right? Or I mean, perturbative. Or the nice thing about this, I find, is exact and lots of numerical methods. Yeah. So that's then. But I mean, yes, Polaron transformation I see as one of the points of alternatives to compare with. Yeah, absolutely. In particular, if you're interested in actual results for a certain setting, you should look with what method you go the furthest in your regime of coupling strength or point of interest. Yes.
Right. If there are no more questions, thank you.
Thank you.